Derek thought I was going to forget to record. But no, also thinks that I was. What about you, Jenna? Did you think I was going to? Jenna had faith in me to record today's lecture, whereas the other two terrible students here in the class in person have no faith in my ability to remember to record. All right. So first thing that we're going to start with today is this thing called the convergence theorem for power series. It should be pretty straightforward. We've already seen some stuff about when does a series converge, right? We know that if we can find that that common ratio, right? We know that if we can set that thing less than r, right, or less than 1 or whatever it might be, right? That was our value before. We should be able to find the interval of convergence. Okay, and a series may do 3 different things. So it may converge. I think the first one I wrote there. It may converge for some limited number of values, right? It may have some sort of like finite interval of convergence from -2 to 2, right? And if we say that it converges from -2 to 2, that would mean that the center of that would be 0, and that the radius of convergence, that's what that capital R that we're going to see here is, that capital R radius of convergence would be 2, right? Because we're going from 0 to 2 and from 0 to -2. From the center of that interval to the endpoints of that interval is 2 units. The radius of convergence is 2. So if we can break it down so that if we have a power series where we can find that value of R such that absolute value of x minus a, so just a single x, not a 2x or not a 1/2 x or not an x squared, but the absolute value of x plus or minus some constant is less than R, we know that it will converge between a plus and a minus R, and that the radius of convergence is R. That's the first thing that could happen for convergence. The second thing that could happen for convergence is it could converge for all real x, or for all complex x. But we're really, like I said, only concerned with real numbers here in this class. So it can converge for all x. We would then say that the radius of convergence is infinity. And that's something that you do want to note, that if it converges for all x, that your radius of convergence is infinity. And because they may ask you what's the radius of convergence, and then it'll converge for all x, and so you'd say it's infinity. So like sine x, cosine x, e to the x, those functions that we've dealt with, those ones converge for all x, so we would say that the radius of convergence for those is infinity. Everybody good there? And then the last thing is that it may only converge at a, so one singular value. And we'll note that up here, like x minus a, right? If it converges at a, that's going to just be what series? If x equals a, what is this series going to be? No, if x is a, c times 0 to the n, and what's 0 to the n? 0, and what's c times 0? So this is just a sum of a bunch of zeros, right? If x equals a is the only place where it converges, we're just saying that that this series is 0 plus 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 0, and then infinitely forever, and therefore that's going to converge because it's just 0, right? We're never actually adding anything into it. Okay? So those are the 3 possibilities for when a series, or for on what values a series might converge. It might converge on a finite interval, it might converge on all real numbers, and it might converge simply at one single value. Any questions or issues with that? People at home good with that, or questions on that? People here good with that?
We're good.
Okay, cool. All right. So I believe I briefly mentioned this way back when, but the nth term test for divergence. The nth term test for divergence is just a test to show if something diverges. This is no longer necessarily about just power series, right? This is just about any series that we might have that's just some set of numbers. The nth term test for divergence, if the limit as n approaches infinity of the nth term of your series is not 0, then that series must diverge. And we talked about that way back at the beginning, right? So what we're going to be looking at today, and if we have time tomorrow for the quiz and for the first couple days next week, is just all of these different tests that are going to help us tell when a series, if a series converges, what interval it converges on, and if the endpoints of that interval converge, and all of that assorted stuff. And so here's just a simple one that will easily tell you that it diverges. If you take the limit as n approaches infinity of the nth term and it's not 0, it diverges. If it is 0, it might converge and it might diverge. We don't know, right? But it can just tell you if it diverges, right? Or if that limit doesn't exist as well. Easy enough. Okay, cool. Spectacular. So now we're going to get into the first of our sort of like pretty important tests here that we're going to have to look at. We're going to use the integral test to prove some good tests, to prove some things about series, and then we might have to use it randomly. So if we have a sequence of positive terms that are decreasing, so we have a positive decreasing function, then we can take the terms of a sequence or a series and write them as a function and integrate that function towards infinity. And if it converges, then the series will also converge. And if it diverges, then the series will also diverge. And this is called the integral test. So as long as, and we're going to use this capital N as an index. So we're going to say it doesn't matter what happens before capital N. It doesn't matter what happens between 1 to 73. If at n capital N equals 73, after that, f is both a continuous positive and decreasing function, and the series is all positive terms, the series that is, can be used to write that function, then this is true. So it doesn't have to always be true. It just has to be true from a certain value within that function. Okay, so it could be doing whatever, who cares what it's doing until I get to capital N, and then at capital N, it's now positive and decreasing forever. Yes, integrable, yes. You have to be able to integrate that function. That is also true. Yes. All right, so if the integral converges, the series converges. If the integral diverges, then the series diverges. First important rule. And as we go through all of these rules, you're going to want to note the criteria that must be met in order for this test to work. And most of them, the criteria will be a positive, a series with all positive terms. This one requires it also to be decreasing. Okay. But most of them will require to be continuous and positive. This one also requires continuous, positive, and decreasing. Okay. So let's see if we can use this idea to figure out if this series, the sum from n equals 1 to infinity of 1 over n root n converges. Any thoughts on how we will do this? All right. Hopefully we will use the integral test for this, since that's the test we just talked about. Yep, that's a good thought. Now, is this, if I were to write out the function f of x equals x to the negative 3/2 or 1 over x to the 3/2, is that series always positive? Will I always get positive terms out of that? Okay. From 1 to infinity, is it continuous? Yep. And is it always decreasing? Right, if I put in 1 to this, I get 1. If I put in 2, I get 1 over 2 root 2, which is smaller, and then 1 over 3 root 3, which is smaller, and 1 over 4 root 4, which is smaller, and 1 over 5 root 5, and so on. Right? So this is continuous. It is positive. It is decreasing. Okay. All three of the initial criteria are met. So we can determine that this series will converge if the integral converges from 1 to infinity of this function. And we will be able to confirm that it diverges if that integral diverges. So what we will do is we're going to look at the integral from 1 to infinity of n, well, it's not n, but x to the negative 3/2 dx. Okay? Which we should rewrite because this is an improper integral. So it needs to be rewritten. And if you're doing this on the AP test, make sure you rewrite the limit as a approaches infinity of the integral from 1 to a of x to the negative 3/2 dx. Good? Okay. And then we will integrate. Everybody at home in Zoom good? Zoom good?
Yes.
Okay. All right. So we integrate x to the negative 3/2. That goes up to x to the negative 1/2. And we divide by negative 1/2, which is going to make this negative what? Negative 2 over root x. Everybody agree with that? From 1 to a, which is going to give us negative 2 over root a. Oh, I forgot my limit. Limit as a approaches infinity. Limit as a approaches infinity. Of negative 2 over root a minus negative 2 over root 1. And as a goes towards infinity, what is negative 2 over root a? 0. And we have minus a negative 2, which gives us 2. So since this came out to be 2, the integral converged. Therefore, the sum from n equals 1 to infinity of 1 over n root n also converges. And we will state by the integral test. And we will make sure to state the test that we use, and we will make sure to list out the initial criteria that must be met to use that test at the beginning. Everybody good there? Okay. Now, what this does not mean is it does not necessarily mean that this series equals 2. Okay? It does not mean that. It's possible. It does not mean that. It just tells us that they both converge. Okay? So do not just say, oh, that series converges, it equals 2. No, that series converges. Okay. Everybody good with that? Okay. All right. And so we talked a little bit about this, I think, or maybe I said we'd prove it when we did series, what we call the P series test. And it will apply for any series of the form sum from n equals 1 to infinity of 1 over n to the p. Okay? And so using the integral test, we can prove that this series will always converge if P is greater than 1. And it will always diverge if P is less than or equal to 1. We could go through and show it. How many of you will be, I feel like, I can't remember if when we were talking about improper integrals, if we proved this back then or not. No? Well, if you think about it, we just did a case with the value of P being greater than 1. And for any value of P greater than 1, this thing should come out to be we'll just really quickly sort of think through it. This would become an integral of n to the negative P, right? And so what we would do is the integral of this would become n to the negative P plus 1 over P plus 1, right? And if we were to do that, we would note that if we plug in, if P is something greater than 1, I'm sorry, negative P plus 1, yeah, sorry, over negative P plus 1. If we were to plug in something that is greater than 1 here, this thing is always going to come out to be convergent. But if we were to look at something like P equals 1, then the integral of that, if P is 1, our integral of 1 over n to the P is going to equal natural log, right? Because that's just 1 over n. That's just going to be natural log of n. And when I do my going towards infinity, I'm going to have a natural log of infinity, which is going to make that diverge. And the same thing's going to happen with something less than that. Like if I have a negative 1/2 down here, and I go up to positive 1/2, well, then I'm going to have this positive power up in the numerator. So P greater than 1, we're going to have a power in the numerator over our negative P plus 1 in the denominator. And this power is going to, as we go towards infinity, go towards infinity, right? And this is just going to be a constant. So this will diverge. And then up here, when we do our n to the negative P plus 1 over negative P plus 1, if P is less than 1, we're not going to have, we're going to have a negative exponent up here still, so that this negative exponent will drop to the denominator, and we will get a finite value out from that integral. Does that make sense to everybody? Yeah, I mentioned it, and I think I was like, well, we might prove it later on with the integral test and blah, blah. So using the integrals of 1 over n to the P, you can see that these things should be true. You guys at home good with that or not? At home, are you okay with that or no? Are any of you even there?
Yes, sounds good.
Okay, so this is called the P series test. It comes directly from the integral test, but you don't need to state integral test if you use the P series test to prove convergence or divergence on the AP test. Just say, this converges by the P series test, or it diverges by the P series test. And it is pretty common for one of these to show up on the AP test where you need to use a P series to figure it out. Good? Everybody good? Okay. All right.
I have a question.
Yeah.
Would that mean if n is raised to any like positive exponent, like not 1 over n, but it was just like n to some exponent to any positive exponent, would that mean it would always diverge?
Say that again. If it was 1 over n to what?
No, if it wasn't 1 over n, but it was just like n to some exponent p, and that it was like a positive p exponent, that would mean it would always diverge, right? Like n cubed or something. Okay.
That will definitely diverge. Correct.
Okay. Thank you.
All right. So the next test that we're going to talk about is called the direct comparison test. So note that the initial condition here is that the series that we're looking at needs to have no negative terms. So it has to be either all positive or zero terms in the series that we are looking at. Okay? We can say that that series that we're investigating will converge if we can find some other series, C, that also converges, and our series is always less than or equal to C. Okay? And we state that it has to be less than or equal to it for all values of n that are greater than some n, right? So again, as long as, if my series that I'm looking at is 73 plus, 101 minus 68 plus 1/2 plus 1/8 plus 1/32 and so on. And I know that I have this other series that is, 100 plus 42 plus 7 plus 1 plus 1/2 plus 1/8 plus 1/32. It's going to follow that same pattern. And we note that after n equals 1, n equals 2, n equals 3, at n equals 4, my series is always less than term by term the other series, if we assume that it's going to continue in this same manner afterwards. Doesn't matter what's happening over here. These numbers don't matter because a finite number of terms of my series will always be some number, right? Doesn't matter if this is bigger than this, or this is smaller than this, or this is negative and this is positive. This is a finite piece, this is a finite piece. And after that, as long as this thing up here converges, then this, which always has smaller terms in it, will also converge. And so if this converges to something, then this converges to something, and the piece of it that converges to that can just be added to this chunk that comes before n equals 4. Does that make sense? That's so that when I talk about n greater than some capital N, this just has to be true starting at some point. Yes, Kevin, this is the same as the series comparison test. Yeah. Direct comparison or series comparison test is the same. Yep. All right. And that should make sense because if this thing converges, right? If this converges, then something that's smaller than it, always smaller than it or equal to it, should also converge. And then the same goes if for some n greater than capital N, we have terms that are larger than some other series and that other series diverges, well, then we know that ours also must diverge. Okay. So what's a series that we know diverges? A series that we know diverges is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Why does this diverge? What is this series? This is the series 1 over n, right? This is the sum from n equals 1 to infinity of 1 over n. Why does that diverge? Diverges by the p-series test, right? Because this is 1 over n to the p, with p equal to 1. Diverges by the p-series test. So if I have that series that I know diverges, but my series is, we'll just multiply all these by 2. 2 plus 1 plus 2/3 plus 1/2 plus 2/5, and so on. Term by term, every single one of my terms is greater than or equal to this other series that I know diverges. So I don't need to do anything else except say that this diverges by direct comparison, or by the direct comparison test, or by the series comparison test, that'd be fine too. And we would generally want to state why this other series also diverges. So we'd say this one diverges by the p-series test, so this one diverges by direct comparison. Does that make sense, people here? Yeah. At home, does that make sense?
Yes.
Wonderful. All right. Let's take a look then at this and prove that it converges for all real. First thing that we might try to do is we might just use the nth term test for divergence just to see if it does diverge. I mean, we're asked to prove that it converges for all real x, so we should be pretty certain that it does. But the nth term test for divergence could immediately tell us, no, this does not converge for all real x. It doesn't converge at all. So the nth term test for divergence says, look at the limit as n approaches infinity. As n approaches infinity, I have exponential over factorial. Factorial grows faster. And therefore, the limit as n approaches infinity of x to the 2n over n factorial squared is 0. And if it's 0, that tells us that it might converge. So let's see if we can find a good series to compare it directly to. Any thoughts? Okay, sine or cosine x is one that we could think about that converges for all real x, right? That's one option. What's another option? Or that's two options. What's a third option? We have three that we know converge for all real x. The series for sine, the series for cosine, and the series for e to the x. So let's think about that. Which one seems like it looks, of those three, most similar to this? I got an e to the x from the chat and a cosine x from people here. What does the cosine x series look like? -1 to the n, x to the 2n. Okay, so we got something weird going on here. This one is alternating. Okay, we need our series to have all positive terms. Is that going to have all positive terms? No, so we can't use that one. So let's think about e to the x. That's what Drew said there. Ryan said e to the x. So let's think about e to the x, right? The sum, we'll say e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. Okay, that's close. That's almost the same, except I have a squared and I have a 2n. Well, using the basic idea for manipulating our Taylor series, what can we do to get an x to the 2n up there? We could just say e to the x squared should be the sum from n equals 0 to infinity of x to the 2n over n factorial. Would you all agree with that? That's the series for x to the, or e to the x squared. Okay. And what does this do? Does this converge for all real x? What did e to the x converge for? E to the x converge for all real. So e to the x squared, that's going to converge for all real also. And, well, what do we know about this series? The sum from n equals 0 to infinity of x to the 2n over n factorial in comparison to this series, the sum from n equals 0 to infinity of x to the 2n over n factorial squared. Right. N factorial is less than n factorial, or less than or equal to n factorial squared. Would you all agree with that? Right. This one should always be less than or equal to this one, right? Because our denominator is always going to be larger. If our denominator is always larger, then our entire thing should always be smaller. So x to the 2n over n factorial squared is always less than or equal to x to the 2n over n factorial. And since this converges for all real x by direct comparison, the sum from n equals 0 to infinity of x to the 2n over n factorial squared converges. Good or no? Okay. Everybody feeling all right so far? Everybody's good through that? Zoom, good? Zoom, good?
Good.
Good, Zoom. All right. Class good? Good class. Okay. All right, let's then, because we've already probably noted that we got this direct comparison test, which requires us to have positive terms. And we already had a little bit of an issue with that because you guys wanted to look at cosine, right? But cosine, the series for cosine didn't have all positive terms. So what we're going to do is we are going to show that if we take the absolute value of a series and it converges, then that also means that the initial series that we started with will converge as well. Effectively, we're going to say that absolute convergence, and absolute convergence is just defined as if the absolute value of the series converges. That's what absolute convergence is. Absolute convergence implies that the series itself converges. So what we're going to do is we're going to start with a series a sub n, and we are going to make this, I think, fairly obvious statement that a sub n is always less than or equal to the absolute value of a sub n, and that a sub n is always greater than or equal to the opposite of the absolute value of a sub n. So if a sub n already has all positive terms, then this is clearly true because they're all just, I mean, the two on the right are equal to each other and the one on the left is all negative, and so it's clearly less than. If these all have negative terms, well, the same thing is true, right? Except that the two on the left are equal to each other and the one on the right is different. And if a sub n alternates between positive and negative terms, then a sub n is going to have some value, whereas a sub n's absolute value is going to be bigger because all those negative values will become positives. And then the other one on the left should be smaller because now every single term is negative instead of some being negative and some being positive. Does that make sense? Everyone good with that basic inequality? All right, so here's what we're going to do. We're going to start off by adding to all three pieces of this the absolute value of a sub n. So what does that give us on the left? Should give us 0. And in the middle, we should have this a sub n plus absolute value of a sub n. And on the right-hand side, we should have 2 absolute value of a sub n. Okay. Now, a couple of things here. Number one, note that we are starting with the assumption that the absolute value of a sub n converges, right? If this series of absolute value terms converges. Okay. So what can you tell me? Oh, that should be a less than or equal to. What can you tell me then about 2 times the absolute value of a sub n? If this series converges, the series that is the absolute value of a sub n, this converges, right? What can you tell me about 2 times that? It should also converge, right? Because what is the absolute value of a sub n? It's some number. It converges to some number. I don't care what number it is. be any number you want it to be. You multiply that number by 2, still converges. True? Right? Still just a number. So this converges because the sum of the absolute value of a sub n converges. That was what we were assuming. Okay? Well, if this converges, and this, which is always non-negative, true? This is always positive. This is always positive. What can you tell me about this? This will if it is less than something that converges, less than or equal to something that converges, and it is always positive, then this must also converge by direct comparison. Everybody so good so far? Good with that? Okay. What if we said then the absolute value of a sub n plus a sub n, and then what if I then subtracted the absolute value of a sub n from that? Could I do that? I mean, that's something I could do, right? I could just subtract something, right? What does that do? That just gives me a sub n, which is what I was trying to figure out if that converged. Well, this is convergent, right? We just said that. It's just some number. What is this? This converges, isn't it? It's just some number. Well, what's some number minus some number? Some number, right? This thing must also converge because it's just some number minus some other number. Okay? So we can then say that if the absolute value of something converges, the series itself will also converge. And that is going to be exceptionally helpful to us because pretty much every single test that we're going to deal with series to test for convergence will require us to have positive terms. And many of our series will be alternating, but we can get around that by just taking the absolute value of it. We take the absolute value, now it's a positive series. Now we can test and see if it's convergent. If it is, we can go back and say our original series also converges. Everybody good there? Everybody in class good with that? Everybody at home good with that? Zoom good?
Zoom good.
Good Zoom. All right. Let's then see here now if we can show that the sum from n equals 0 to infinity of sine x to the n over n factorial converges for all x. And the first thing we're going to think about as we do that is what? What's the first thing we're going to think about? What? Yeah, we're going to say, well, it doesn't necessarily alternate, but we can say that for all x, what can you tell me about this series? These terms are, well, okay, so yeah, so say that they're between -1 and 1 for the sine x part, right? Which means that there are sometimes terms that are negative. So we will say that the terms are not all positive. Okay? The terms of this are not all positive. Therefore, we cannot just use the direct comparison test with this because for some x, we get negative terms. Everybody good with that and understand the reasoning why we can't just go straight to the direct comparison test here? Okay. So then let's look at this. The sum from n equals 0 to infinity of the absolute value of sine x to the n over n factorial. Does that have all positive terms? It darn well should. If I put an absolute value around it, it's definitely going to have all non-negative terms, right? It's going to have all non-negative terms. And if we can prove that this converges, then we should be able to say that the original series itself also converges. Correct. Yes, logically it makes sense why, if the absolute value converges, the rest, the non-absolute value does not. But we have to have a rigorous proof of it. What we did was not super rigorous, but at least a proof. So what are we going to do now that we have this sine x to the n over n factorial inside of an absolute value? Noah before made a good point about sine x. Right. Noah said that sine x is always less than or equal to 1, greater than or equal to -1. And that when we take sine x and raise it to a power of n, what happens to that? Right, but 1 to the n, -1 to the n, those are still just going to be between -1 and 1. True? I mean, if I take a number that's between -1 and 1 and raise it to any power, it's never going to get larger than 1 or less than negative. Would you all agree with that? Zoom good? Zoom is good now. Noah says Zoom good.
Zoom good. Man
Zoom
walk.
good. What?
Man walk.
Man walk. Man walk, Zoom good, good Zoom. Okay. All right. Now, what about then the absolute value of sine x to the n? Because we do have an absolute value on it. That's always going to be less than or equal to 1, greater than or equal to 0. True? But even better, we can say that the sine x to the n inside the absolute value is just between 0 and 1. All right, how did that help us? We can do stuff now, Derek says. Okay, that's right. We can do stuff now. Okay. We have a number that is always between 0 and 1, and it is over n factorial. What is the largest possible value that that numerator could be? No, the largest value that the numerator could be. The largest value that that numerator could be is 1. So you should be able to tell me then that this series is always, no matter what, 100% of the time, less than or equal to the sum from n equals 0 to infinity of what series? If you know that, what? 1 over n factorial. Would everybody agree with that? Zoom good? Y'all agree?
Zoom good.
Zoom good. Good Zoom. Okay. Well, how did that help me? I mean, if 1 over n factorial converges, then sine x to the n over n factorial must converge, or the absolute value of it, and then therefore the sum. You cannot use the nth term test for divergence to show that it converges. If you try to use the nth term test for divergence, you'll see, well, it might still diverge, but we can't be guaranteed that it diverges. But what do we got? 17 minutes. I want you guys to have to think a little bit here. So I'm not going to say anything for like 45 seconds. I'm going to sit here, and I want you guys to look at it and think about other series that we've used in the past. Okay, say that again. Okay, Noah has said that there's something in there about x to the n over n factorial. We dealt with the series that had an over n factorial. E to the x, right, we said was the sum from n equals 0 to infinity of x to the n over n factorial. Everybody agree with that still? This we know converges for all x, right? But I can't just use the x to the n over n factorial, because sometimes x could be less than 1, couldn't it? Right, I can't just say, well, because x to the n over n factorial converges, then that means that this sine of x to the n over n factorial converges, or even that 1 over n factorial converges, because sometimes x to the n over n factorial is less than 1 over n factorial, and sometimes it's greater than 1 over n factorial, depending on the value of x you choose. Well, that's okay, because we know this converges for all x. So pick an x. We'll say, no, okay, 0 we could choose, but that's not going to work. Including x equals 1? True? Including x equals 1. Well, if x equals 1, this is the series from n equals 0 to infinity of 1 to the n, which is 1 over n factorial. And what do we know about this? This converges. True? We know that 1 over n factorial converges because that's just x to the n over n factorial at x equals 1, which is a value at which it converges, since it converges for all x. Does that make sense to everybody? Cool. So this, we'll say, converges. And therefore, so by direct comparison, and I'm going to say, you don't have to necessarily write this because you've done it a bunch of times, but I'm going to say with n equals 0 to infinity of 1 over n factorial, the sum from n equals 0 to infinity of the absolute value of sine x to the n over n factorial converges by direct comparison. And then we will say, so the sum from n equals 0 to infinity of sine x to the n over n factorial also converges. I will ask you to write because absolute convergence implies convergence. Good or no? Good. Wonderful. Zoom good?
Good Zoom.
Good.
Zoom good, good, Zoom. Okay. So that's how the direct comparison test works. You got to find some series, and it requires sometimes a little bit of creativity. First, are the terms positive? Yes? Good. Move ahead. Are the terms not positive? No? Okay, take the absolute value. All right. Then find a series that you know converges that is always greater than or equal to your series. It might take a little bit of thought to figure out that series. Or does your series, if you think your series diverges, find a series that diverges that you know is always less than or equal to your series, and compare them together. And hooray. We'll figure it out. Everybody good or no? That's wonderful. All right, the next, and I would say the most important test that we are going to deal with this year is called the ratio test. Okay? So the ratio test. Normally I go through and prove this, but I don't think we're going to go through and prove it this year just because we are really, really running short on time for the couple of people that are doing the May 4th test. I want to make sure we get a chance to use it quite a few times and get through everything more quickly. So the ratio test says if you have a series A sub n with positive terms, note that that important criteria again, positive terms, that if you take these limits as n approaches infinity of the n plus first term divided by the nth term, and that limit is less than 1, the series will converge. If that limit is greater than 1, the series will diverge. And if that limit equals 1, well, that sucks for you. You've got to find some other test to use. a lot of the time, it will, I mean, I would say most of the time for what we will deal with, it will fall into choices 1 or 2 there, where it will not be inconclusive. The ratio test is a favorite test of them to use on the AP test in the free response. Okay? They like to throw out the ratio test at you to prove that something converges or diverges. Okay? So like I said, if you want, you can go in. I'm pretty sure I proved it during the period 1 lecture, so I can try to find the lecture in which that happened if you want to go watch it, if you are just genuinely interested in like why these things work, which you should be, I hope, but some of you probably don't care. But if you want to, you can go watch the old lecture. But very important test. Positive terms, find the limit as n approaches infinity of the n plus first term over the nth term, and see what you get. Okay? If it's less than 1, like I said, converges, greater than 1, diverges, equal to 1, inconclusive. So there's our proof. I'm not going to do the proofs. All right, let's see if we can find the radius of convergence, and really what the interval of convergence there then is for n x to the n over 10 to the n from n equals 0 to infinity. So first thing, what should we do? What am I? What should we do? No.
See if all the terms are positive.
See if all the terms are positive. Does this have all positive terms for all x? No. Not positive for all x. So what will we do? We will look at the sum from n equals 0 to infinity of the absolute value of n x to the n over 10 to the n. Everybody good there? Okay. Now, definitely all positive terms. Okay. Now what will we do? We will jump straight to this ratio test. So we are going to look at the limit as n approaches infinity of the n plus first term of this series divided by the nth term. So I'm just going to put a big old absolute value there. The n plus first term, so n plus 1 times x to the n plus 1 over 10 to the n plus 1 all over the nth term, n x to the n over 10 to the n. Good? N plus first term, so replace n's with n plus 1s. Nth term, just leave them as n's. Good or no? Okay, let's simplify. We end up with n plus 1 x to the n plus 1, and then this 10 to the n is going to get thrown up into my numerator, right? And then in the denominator, I'm going to have 10 to the n plus 1 n x to the n. And now we should be able to simplify that down. How will we simplify that down? Different man walk. I know, it's weird. Why are they just walking around here? I don't know. All right, what do we get here? What can we simplify? Can I simplify x to the n plus 1 over x to the n? Yeah, what does that simplify to? X. X to the n plus 1 over x to the n is x to the n plus 1 minus n, right? Just x to the first. What about the 10 to the n and the 10 to the n plus 1 in the denominator? That can just become a 10 in the denominator. What about the n plus 1 in the numerator and the n in the denominator? Can I simplify those? No. But what happens as n goes towards infinity? N plus 1 over n, that +1 becomes insignificant as n goes to infinity. The limit as n approaches infinity of n plus 1 over n is just 1. And so the limit as n approaches infinity of absolute value of x over 10 times n plus 1 over n should be absolute value of x over 10. Cool. Everybody good with that? Okay. That's your limit. Now, the question is that limit less than 1? Is that limit greater than 1? Does that limit equal 1? Well, it's hard to say, isn't it? It depends on x, right? So that's what we're trying to do, is find this radius of convergence. So what we just need to do then is make this less than 1 and see when that's true. So we will set this less than 1. That tells us that the absolute value of x is less than 10. And that will tell us that the radius of convergence, way back from our very first convergence for power series slide that we had, that the radius of convergence is 10. You guys good with that? Because we had the absolute value of x minus a is less than 10, or is less than r. So our r is 10. That radius of convergence is 10. And we could say that the base interval of convergence for this is -10 to 10, right? That our series, that our absolute value and our series will converge from -10 to 10. We wouldn't be so sure about the endpoints yet. We would need to check the endpoints. We're not going to check the endpoints yet until we have a couple more different tests underneath our belt that we can use just in case we need some other ones we haven't learned yet. Sound good? People here good? Zoom, good?
Yes.
Good.
Good, Zoom. All right. We got time. Let's do another one. The sum from n equals 0 to infinity of n factorial times x to the n. Good. I'm glad, Noah. Take that. Now you're suffering. Message, you're suffering. Yeah, you're a sucker too. Just kidding. Haha, that was a joke. That's right. Yeah. Exactly. Just kidding. Just kidding, Zoom recording. Ha ha ha. Just kidding. No, I didn't say do it on your own. All right. First thing we should look at is what? Is it all positive terms? Are they all positive terms for all x? Not positive for all x. Not really, not greater than or equal to 0, but that's fine. Not positive for all x. All right, so we'll look at the sum from n equals 0 to infinity of n factorial x to the n inside absolute values. And we'll use our ratio test. The limit as n approaches infinity of, well, let's see here. N plus 1, that term would be n plus 1 factorial. X to the n plus 1. No. N factorial x to the n. Close, but no. Yeah. Okay, so we have n plus 1 factorial over n factorial x to the n plus 1 over x to the n. What does that simplify to? Be an x in the numerator, and right. We did. We went over what is n plus 1 factorial over n factorial. And somebody in the chat has said, yes, exactly, Ryan, it is just n plus 1. Okay. And this limit equals infinity if x is not 0, right? But if x is 0, then this limit is 0 because it's 0 times n plus 1, which is 0. And then you're looking for the limit as n approaches infinity of 0. Well, the limit as n approaches infinity of 0 is 0. So this is infinity if x is not 0, but it equals 0 if x does equal 0, which tells us that our radius of convergence is 0. Radius of convergence is 0. There is only one singular value of x that makes this true. It is x equals 0, which if we wrote x as x minus a, tells us that we're getting that a minus a, right? It only converges at that value that is at the center of our interval of convergence. Way back from that very first slide. Good? No, you don't need to, you don't need to write using the ratio test. It'll be pretty clear that you use the ratio test. That's fine. All right. I think we probably need to stop because we have 1 minute left and we probably won't make it through another problem. So we will do a couple more with the ratio test tomorrow after the quiz if we have time. And then we will move forward into the last couple of tests and work on testing at the endpoints and all of that fun stuff to find the full interval of convergence. Well, somebody said something in the chat. We have to go through all the steps of different ways, and we just jump straight to the as in, you mean writing it out in the absolute value? Like, do you have to like state that it's not positive? Is that what you're asking, Kevin?
No, like on the AP test, it's like if they ask for this and they want you to show your work, like can we just jump straight to the fact that like radius of convergence is the limit of the nth term over like the coefficient of the nth term divided by coefficient of the n plus 1?
No, they're gonna want you to show that you wrote out what the that you wrote out the n plus first term over the nth term, and then show the simplification of that, and then state the limit. They're gonna want to see all the steps. They usually give, not always, but sometimes they give points for like each intermediary piece of it. So if you want to show it all.
Oh, so you can't just use that fact, even though like it's like it's true for like all series, right?
Yeah, you're correct. It is true, but they still want you to show it out, and if you don't, they won't give you the points. So.
Okay.
Yeah. Anybody else in Zoom questions? Otherwise, you are good to go.
Could you go back to the last slide real quick? So could you explain how you got from limit as n approaches infinity of x times n plus 1 over 10n to the x over 10?
Yeah, so you think about this, this is just a limit. You can separate a limit into two different pieces being multiplied together. Right, so you could rewrite that as the limit as n approaches infinity of x over 10 times the limit as n approaches infinity of n plus 1 over n. And then n plus 1 over n as n goes towards infinity approaches 1.
Wait, could you explain how that approaches 1 to n plus 1 over n?
Yeah, that's just, I mean, it's infinity over infinity, right? So you can use L'Hopital's rule.
Okay, yeah.
Derivative of the top and the bottom gives you just 1. Or, I mean, it's just the horizontal asymptote basically of a rational function. So,
Okay.
yeah. Does that make sense?
Yeah, thank you.